Okay, good morning everyone and welcome to today's webinar on catalyst-based non-chemical scale prevention. Before we get started with the webinar, I want to go over just a few webinar logistics. And for the presenters, we want to make sure that when we're not speaking, we have our phones muted. Everyone else is muted during today's presentation. So today's webinar is based on a report that's available on the GSA website, and the full report as well as a 4-page findings and a 1-page infographic are here. You can also find a list of upcoming GPG outbriefs. They always occur Thursdays at 12 p.m. Eastern Time, and you can find a list of upcoming webinars at gsa.gov as well as recordings of past webinars. In October, we'll be hosting a webinar on our assessment of a wood pellet-fired biomass boiler that was installed in Ketchikan, Alaska. And this technology was found to be a cost-effective strategy for facilities that are currently relying on fuel oil. In addition, GSA was really interested in it to find a way to take advantage of the waste wood that has been accumulating in the forest because of the pine beetle infestation. And so that next webinar will be October 12th. In November, we'll be hosting a webinar on multiple GPG assessments of electrochromic windows. GPG has been looking at these windows for a number of years now. We'll be releasing 2 new reports in the next month. EC windows are dynamic windows, and they respond in real time both to weather and to user preferences to change the window tint, kind of like smart sunglasses. In December, we'll be hosting a webinar on 2 next-generation chillers that GPG has assessed, both the variable speed magnetic bearing chiller and the variable speed screw chiller. Both of these chillers are 35% more efficient than FEMP-designated chillers, and both were found to have payback under 5 years when replaced at end of life. Next year, the first webinar we'll be holding is on socially driven HVAC optimization. This technology uses input from occupants for dynamic temperature management, and the results from the assessment showed that occupants were more satisfied with their thermal comfort as well as that it saved energy. In February, we'll be hosting a webinar on plug load control and advanced power strips. Now, these dates, we're always holding webinars Thursdays at 12 p.m., but the dates may shift, so check both. You make sure you're on our mailing list to get invitations to sign up for the webinars and to register for the webinars, as well as you can check back at gsa.gov for the current list. All GPG webinars now offer continuing education credit, so to receive credit, you can complete the post-webinar survey, and if you don't receive a survey, please contact Michael Hobson at michael.hobson@gsa.gov. Today's broadcast is set to listen-only mode, so you can chat questions here in the right side of your screen in that chat window. And you don't need to wait for the Q&A segment at the end of today's session. It's great if you want to submit your questions all during the session. And now, to get started with today's webinar, Mike Lowell will be facilitating today's presentation. Mike.
Next slide. Welcome, I'm Mike Lowell, Project Manager for GPG. Today's webinar will include a brief overview of GPG by Kevin Powell. After this overview, Dan Howlett from the Oak Ridge National Laboratory and the primary investigator for the GPG assessment of catalyst-based non-chemical scale prevention will summarize the research results in Salt Lake City. Dan's presentation will be followed by on-the-ground feedback from Daniel Long. We will end the webinar with an interactive Q&A session. Next slide.
I think that's the transition to me.
Yes.
This is Kevin Powell, and I am the Program Director for Emerging Technologies at GSA. Next slide, Andrea. The Emerging Technologies program at GSA includes our GSA Proving Ground. And the GSA Proving Ground was established to help our agency make sound investment decisions in next generation technologies based on their real world performance. So when GPG adds a technology to its list of recommended technologies, it's already been vetted. That is to say, we know it can be installed, we know it can be operated, we know it's going to deliver its claimed performance in the real world in our portfolio of buildings, of federal buildings, and that it has good financial payback, and perhaps most importantly, to the degree that it interacts with our network, it's cyber secure. Next slide. Yep. So this, of course, is an image of that is often referred to as the technology valley of death. And what we know is that there is a tremendous amount of innovation going on in the area of commercial building technologies. And a lot of that is driven because both the market, in terms of owners such as GSA, as well as innovators, such as in this case, Fluid Dynamics or anybody else, want to make a better building than the last one. And we're constantly being challenged to do more with less. Innovation is what drives the efficiencies that let us do that. The challenge is that 4 out of 5 technologies that essentially come to the marketplace never cross this technology valley of death. That is to say, they never get beyond the early adopters, the adventurous folks. And what our GPG program is designed to do is to help bridge that gap. We do that by leveraging the federal government's portfolio of office space. We're the largest commercial building owner in the country, in terms of our portfolio, single portfolio. And that scale lets us do the research required to vet these next generation technologies and to have confidence in their real world performance, as I just said. So there's a couple of other programs that we work with, the Department of Energy's Better Buildings program, which looks to drive uptake of these next generation technologies with the private sector, with private sector owners. And we have a sister program over at Department of Defense, the ESTCP program, which also proves out next generation technologies that are applicable to onshore military facilities. I think it's also important to note that although we've just really gotten started in terms of deploying technologies that have proved out, they're already delivering really significant savings for our portfolio. So next slide. So just a few notes about our process, and we are, of course, first and foremost, we're a federal program. We're committed to operating in an open, transparent process. Every fall, we publish a request for information. For the past 3 years, we've been doing that in conjunction with the Department of Energy. We are planning to release our next request for information on October 23rd. There'll be 2 topic areas for next year's RFI. First, the words are going to change a little bit, but just generally speaking, first topic is going to be behind the meter load optimization, and the second is going to be improving overall building operations and maintenance. What happens after you apply, and we encourage anybody on the phone who has a technology that might fit into one of those 2 areas to look to this RFI to apply. Your submission will be evaluated by 3 subject matter experts who really have a good understanding of what your technology can do, what its promise is. We then shortlist approximately 20 technologies which are invited to present to us. You're basically presenting to a group of subject matter experts from Department of Energy, Department of Defense, and from GSA. We then select a short list of finalists. That number has been changing based on budget, but it's been anything from 3 to 10. Those finalists are then matched to a location or locations within GSA's portfolio of over 1,500 owned buildings that are best suited to validating real-world performance as we described. Working with Department of Energy's national labs, we then look to objectively assess how the technology delivers on those claims, how easy it is to install and operate, what payback looks like, to the degree it's tenant-facing, how it affects tenant satisfaction, and to the degree that it has an IT component. Can we validate it that we can operate it in a cyber secure manner? We are committed to publicly publishing results that translate into real-world action. That's what this webinar is all about. We want to share with you what these best-of-breed innovative technologies are, and we want to, basically engage with you to share what those real-world results are in a way that can help you have confidence that this makes sense, and to the degree that we have GSA folks on the line, that these can be incorporated successfully into your projects. So we think that this is actually kind of critical in terms of where we are as a country, in terms of where we are as a federal government, in terms of our budget, how do we deliver value to the American taxpayer, and so hopefully you'll find this webinar of value. With that, I'm going to turn this over to Dan Howlett.
Thank you very much, Kevin. Good morning, everybody. My name is Dan Howlett. I'm a mechanical engineer at Oak Ridge National Laboratory. I was the principal investigator looking into this technology that we evaluated in Salt Lake City, Utah. Next slide, please. This technology in particular, what we called it is a catalyst-based non-chemical scale prevention system. The vendor, when they originally brought this technology to the program, they represented it as a complete water treatment system where it addressed both scale and biocides, which is something that you would need on a cooling tower application. We were originally going to test both in a water heating system and in a cooling tower. We ran into some challenges within the project and we were not able to test it on a cooling tower, so we focused on scale prevention. The site where we did the testing is the Frank Moss Courthouse in Salt Lake City, Utah. The challenge that was happening at that site, they had a domestic water heater, a large central domestic water heating system that used electric heating elements, and because of calcite buildup, they were replacing heating elements about every 6 weeks. They were burning up. These are elements that should normally last for years. They were burning up in about 6 weeks due to calcium buildup. So we had the technology that claimed to address calcium buildup. We had a place that certainly had a challenge with calcium buildup. It was time to get started. Next slide, please. A little bit about this technology. Physically, it's very simple. It is, to look at it, it's basically it looks like a spool piece of pipe that you simply insert into the water pipe. Inside is a helical insert of a proprietary metal. They did not share with us what that is. And one point that I would like to emphasize, everything I'm going to talk about on this slide is information that was given to me by the vendor. One of our premises when we do a proving ground evaluation is we focus on results. What are the results of the technology? We don't, how the technology does what it does inside the black box, so to speak, we don't evaluate. So the information I'm giving you on this slide is how the vendor claims their device prevents calcium. So what they claim is that water with a certain amount of calcium and carbon and dissolved oxygen and all that sort of stuff flows through their device around this helical insert, that the water molecules and all the different molecules contact this catalyst, and that instead of forming calcite, which is a material that bonds quite readily with surfaces and causes these challenges, that it forms a molecule called aragonite, which chemically aragonite and calcite are almost the same. The crystal structure is different, and aragonite supposedly does not plate against surfaces as easily as the calcite does. Next slide, please. Here's a little bit more about the device itself. The picture on the right was actually taken at the courthouse. The blue device, except for the blue color instead of copper color, like I said, it does look like a spool piece. The units are sized based upon the flow rate found at the site. We'll talk more about that later. The devices are made as small as 3/8 of an inch, more focused for the home appliance market, ice makers, things like that. They're also sized large enough for industrial applications. This device is proprietary. It's been in Europe since 1973, was brought to the United States in 2010. There is only one manufacturer of this equipment. Next slide, please. This is just a snapshot of why GSA was interested in this particular technology. Hard water is a big challenge in a lot of places. It causes problems, which we're all familiar with. Next slide, please. This is a picture of the Frank Moss Courthouse. It's a beautiful Art Deco facility. If you're ever in Salt Lake City, please stop by. Next slide, please. Now let's get into the details of the actual test. When we got there, we looked at the baseline conditions, which were obvious based upon information given to us by the site. Every 6 weeks, these heating elements, they were coating with the calcite, they were overheating, they were destroying themselves. You can imagine the headaches that presented not only to the end users, the occupants of the building, but to the O&M staff that had to keep going in and fixing this. We set the test up. We were going to run a baseline for about 3 months. We were going to insert, then we were going to take time out, insert a new one of the water treatment devices. That's the silver pipe that you see on the right, the silver spool piece, and then see if it could address the calcite conditions that were building up. Next slide, please. As we started into the baseline portion of the test, the heating elements, they failed after 7 weeks. Not much more we can say about that. You can see the elements on the right as we pulled them out. They were caked with the calcite material. It was very hard. We had to kind of flake some of it off. One of the things that we noticed as we were pulling out these heating elements, one of the team members noticed that this particular device was, the heating elements were designed more for a residential water tank, not for a commercial water tank. Another thing, so we put in our clean elements and we put in the spool piece, this technology that was supposed to reduce calcite, and we ran the test, hopefully trying to see, was there did the calcite reduce? Well, they didn't. The calcite still formed, the heating elements still failed, so we started to explore much more deeply what was going on. Was this technology snake oil? What were the issues that were happening? We started to go through and troubleshoot this system. We looked at, what are all the things that might have caused this to happen. We had already addressed the commercial elements. We had commercial elements in there. The commercial elements were still heating and failing. What we found, and this is a real critical point that I want to emphasize for anybody who is thinking about using this device, what we found was that the original drawings which we used to find out how much water was flowing through the pipe, the recirculating line, The original drawing said that there were 20 gallons per minute flowing through that line. We actually put a flow meter on the line, an ultrasonic flow meter, and we found that the flow varied only between 6 and 11 gallons per minute, not 20 gallons per minute. When looking at this technology and working with the vendor, that took us to a different size of device to put in there. You know, basically as we looked at it and then talking to the vendor, what was happening was because the water was flowing over that helical insert so slowly, what the vendor said was there was not enough turbulence within the water. So the water and the calcium molecules and the carbon molecules were not making enough contact with the catalyst, and it was not forming aragonite. I'm a skeptic, but I'm also a researcher. We followed the guidance of the vendor. We put in a properly sized element, a properly sized device, and we reran the test. Next slide, please. We started over with the baseline. We inserted the commercial elements again, and the picture on the right is of the new 3/4 inch pipe insert. If you remember the previous slide, we used an 1.25 inch pipe insert. That was back when we thought that it was 20 gallons per minute flow. This one, it's sized for the 6 to 11 gallons per minute, so we started to run the test. Again, I'm a skeptic. I spent most of my career designing mechanical systems. Water treatment systems have some of the worst reputations as far as being snake oil salesmen, but I was curious. I need to go where the data takes me. What are the potential outcomes of this device? We redid the baseline test. We did the baseline test by reinstalling elements, and instead of immediately, one thing I need to correct just for clarification's sake, instead of immediately installing that blue insert in there, we reinserted the spool piece. That way there was no water treatment of any sort going through the system again. Next slide, please. As we were going through this second test, after 6 weeks with no water treatment system, the heating elements again caked up and failed. That's the picture on the left. Even the elements that did not burn in 2, they were caked in the process of burning, and they showed signs of damage. We then inserted the blue spool piece, the one that was smaller, the one that was properly sized. And we restored the water heater to service. We let it run. And it ran. And it ran. And it ran. After 3 months, we went in and pulled out the heating elements. Again, this is the first time this water heater has run this long without a failure. The picture on the right shows one of the heating elements that we pulled out after 3 months. There were some tiny bits of scale on it, but absolutely nothing compared to what we had seen. Again, you can compare the left photo to the right photo. I'm a skeptic, but I'm also a researcher. I've got to go where the evidence takes me. Inserting a properly sized device into the line worked. It prevented the calcite from building up within that system. Next slide, please. One of the other things that we were keeping track of was water temperatures as it flowed throughout this recirculating line. You can see here, and to maintain water temperatures within the space, the operations staff had the temperature setting. It wasn't the controls on the water heater were not set to specific degrees. It was just a low, medium, high. They had to keep it set on high in order to maintain the temperatures that customers wanted. What we noticed after the baseline period when we put in this system is that the temperature within the water started to rise. If you think about the equation Q equals UA delta T, the heating element was still trying to put the same amount of heat into the system, but because the thermal resistance wasn't there, the calcite anymore, the element stayed cooler, it didn't burn up, and the water temperature warmed up. It warmed up to the point where the operations staff had to go adjust the thermostat and take it down to a medium setting. And you can see the point on the graph where that was accomplished. Next slide, please. This graph comes from the vendor's literature. And you can see sort of in the middle of the graph how we originally picked an 1 1/4 device sized for between 20 and 30 gallons per minute based upon the information that we had from the mechanical drawings. When we actually put the flow meter on and saw that the flow was between 6 and 11 gallons per minute, that drove us down to the 3/4 inch device. And again, I'm a skeptic, but I've got to go where the evidence takes me. Putting in the properly sized device prevented the calcite from building up and burning out heating elements. Now, one thing, and I know Daniel's going to talk a little bit more about this, after assembling the device, the calcium did not plate out on the heating elements. But one thing that we did notice is that there were calcium crystals that formed in the bottom of this tank, not on the heating elements, but in the bottom of the tank. These were different from calcite that builds up on heating elements. These crystals, they were very loose. They just sort of landed down there. And it's turned out that the O&M staff has to go in, I think it's once a year now, to clean out the bottom of the tank. But the crystals that were formed did not land on the heating elements, and they did not plate out in the pipes. They landed in the bottom of the tank, where they caused no problems. Next slide, please. This is some of the economics. We tried to compare the catalyst-based scale prevention system to a conventional salt-based system. The 3/4 inch diameter unit, its particular unit price was $1,100. To treat the similar amount of water, the salt-based system price was about $2,600. Installation cost was comparable. It took a while to get both systems in. It took a while, especially this catalyst-based non-chemical system. You can see where we estimated the prices. Where the big savings come in going forward is that once it's in, there are no more chemicals required. It just does its job. And as Daniel will talk about, they've got to go in, well, in this case, it's every 6 months, and clean out the crystals in the bottom of the drain. The simple payback period is actually immediate with this. Lower first cost, lower operating cost. Next slide, please. The lessons learned to share with anyone who's considering using this system. Sizing the device is key. As I said earlier, we first ran into problems where we thought the device might be a failure because the heating elements were still burning up. It turns out that measuring flow is really important. It's worth it to go put an ultrasonic flow meter on whatever system you're thinking about using it on to make sure that your device is sized properly. Don't just use what is shown in the mechanical drawings. Also, and this is a side note, if you're using an electric water heater, make sure you're using commercial grade elements. Next slide, please. The best place to use this device is really any place that is having challenges with hard water. We saw really no restrictions as to where it should be used. We tried to determine some sort of a threshold that if you have calcium concentrations above a certain point, then it should really work. We could not, with confidence, come up with that threshold. But basically anywhere where you've got challenges with hard water, this device has potential to help out significantly. With that, I will turn it over to Daniel Wong, Facility Manager.
Hi, everyone. Can you hear me?
Gotcha, Daniel.
Yes.
Okay, thank you very much. My name is Daniel Wong. I am the building manager here at the Frank Moss Courthouse in Salt Lake City, as Dan talked about. I've been the building manager there for 7 years. And when I heard about this technology and it was proposed to be done in our courthouse, I was extremely thrilled with it for the very reasons that Dan was talking about earlier in his presentation. Next slide, please. We've had the device in place for approximately 4 years. It's been calculated that we've saved around in the neighborhood of $57,000. This has been a huge deal for us, primarily because of the fact that we were replacing our elements every 6 weeks as they were burning out. On the right of this slide, you can see the water hardness scale. I pulled this off of the Water Quality Association, and it was established by the American Society of Agricultural Engineers and the Water Quality Association. And you can see that what is considered soft water and then what is considered very hard water, less than 1 grain per gallon is considered soft water. Over 10 grains per gallon is considered very hard water. Click, please. At the bottom there, you can see that the Moss Courthouse water is actually still getting measured regularly between 19 and 25 grains. So the water that we have here is still extremely hard, and the device is continuing to work very well in our building. We're basically on a schedule right now to replace our elements when one fails. And the way that we know when an element fails is that there is an LED on the side of the control panel that when the element fails, it lights up. And so our mechanical staff check it on a regular basis, and when they notice that the light is on, then they go in, they drain the tank, and then we replace the elements. And it ends up being approximately every 8 to 12 months that we're doing this. Typically, it's about 12 months from when we replace the elements to when we have to do it again. While the tank is drained, the mechanics will clean and vacuum out the sediment just so that we don't have a collection of it at the bottom of the tank. They probably don't need to do that every time, but it's something that they like doing so that they don't have to worry about it going forward during the year. One thing to note as it relates to water hardness, we have some tankless water heaters or Insta-Hot water heaters in our building in some of the chambers. My mechanic showed me their warranty, and the warranty on those tankless water heaters is that if the hardness is over 7 grains, they will not warranty the equipment in the building if it fails. So, you know, these companies know about this, and the hard water is a huge issue for us that we're dealing with. Next slide, please. The installation, as Dan talked about, is very simple. It's basically plug-and-play technology. Next slide. As the plumber is doing the installation, he is doing what he would normally doing and creating a spool and putting it in place in the incoming water line to the tank. And you can see that the device is on the ground next to him, and he's removed that piece of piping. Next slide, please. As Dan talked about, measuring the flow is a big deal in this entire process. You need to make sure that you have that right flow. The picture here that you see is when we installed the initial 20 GPM device, and as you know, that failed very quickly. The next slides that I'm going to be showing you will include some pictures that just kind of show what we saw as we were coming into this this test. Next slide, please. So before we actually replaced or put in the device, you can see what the elements were looking like as they were coming out. The elements actually were bending. They were actually opening up because of the heat. My mechanics would use a little hook to pull everything together. Otherwise, they weren't even able to get them out of the tank. You can see in the picture on the right-hand side the type of buildup that was calcite that was coming off of the elements and falling to the bottom of the tank. Next slide, please. This is, again, a picture of the device that we first installed, the 20 gallon per minute device. Next slide. And as a result of that, we had, as you know, within 7 weeks, the elements were failing catastrophically. You can see the buildup on the elements. You can see how thick the calcite is on them, the inside of the tank. And the next slide, you can see how they were kind of destroying themselves and basically breaking apart. Next slide, please. And this is what one of those elements, actually we had, after that first test, I think we had 4 or 5 of our elements that came apart in this way. And you can see the scale, the calcite is extremely thick and extremely hard. Once we got the correct device in place, next slide please, you can see that it is a smaller device there on the left-hand side in blue. And on the right-hand side, that's a picture that I took, I believe it was November of 2014, so after it had been installed for a little while. And you can see the sediment that is built up there on the bottom of the tank. In talking with my mechanic about this, his comment to me was, whatever it's doing something. We do have a little bit more sediment or debris at the bottom of our tank than we used to. But in the past, when we would have a failure with one of our elements in the water heater, typically 4 or 5 of the elements would fail at the same time. And when we pulled them out, they were just in bad shape. Typically now, if one of the elements fails, it is only one element that fails. They last much longer, almost a year now, where we were replacing them almost every 6 weeks before. And then, as we said, and as you can see in the picture, the debris that ends up at the bottom of the tank, while there's a little bit more, it's much finer, and the elements are lasting much longer. So I'll turn it over now, next slide, to Michael for questions and answers.
Thank you, Daniel. And let me switch over to that page. And let's see, question number 1 is from Paul Zambone. Well, first, can everyone hear me?
Yes.
Yes,
okay.
We can hear you.
First question, Paul Zambone. Can GSA folks suggest emerging technology, or is this the responsibility of the private sector? And Paul, I'm assuming you mean for submittal to the program. Assuming that's your question, we get submittals both from GSA folks as well as from private sector. Actually, early in the program in 2011, for our first RFI, all of our accepted applications were internal. And then by 2012, about half of our accepted applications or technologies were internal, about half were external from the private sector. And by 2013, we started seeing, frankly, almost all, if not all, of our technologies coming from the private sector. But that doesn't preclude GSA teams from submitting their technologies to our program. Jack Ziegler asks, what's GPG? And I apologize for that back and forth. GPG, assuming it's in capital letters, typically is GSA Proving Ground Program. And the case of what was on the slide, which I noticed later, was that was gallons per minute. It was a typo. That should have been GPM, not GPG. So apologize for all of that confusion. Next question, Dan Lewis is asking, what sensor was controlling that heating element? regarding, and in quotes, heating element slide 23. I don't know, Daniel, if you can answer that, or I see someone's added a note.
Mike, this is Daniel. So for this particular water heater, we have an LED that lights up when the element fails. I don't know exactly what it is that that causes that to happen, but again, we just wait for that light to light up, and then we go in and replace the element.
Thank you. And Dan Lewis, where would these crystals land in a condenser water system, i.e. chilled water system? And I see Dan Howlett probably. Dan, I'm going to let you read your own answer, or Daniel Wong, I'm sorry.
Yeah, this is actually Daniel Wong. My thought on the debris and the crystals that we're seeing in the water heater is the aragonite, or actually I don't remember what it's called, but the converted calcite that is landing on the elements and then subsequently falling off. When we look at the debris that's in the water tank, it is curved like the elements themselves. I don't, based on my conversations with fluid dynamics while we were going through this, I don't know that the same thing will happen in a condenser water system, but that would be a question that I would defer to the fluid dynamics representative and see what his thoughts are on it.
And
Daniel,
with that,
this
Rob,
is
go
Rob.
ahead.
Yes, yeah, and a condenser, the crystals will typically flow out and go wherever the water is going to go. Like in a cooling tower, it'll go through the blowdowns, out the windage, and typically in most applications, we always recommend everybody, like in the water heater, that they do flush it once a year because there will be some sediment in the bottom. But most of the aragonite stays suspended in the water and goes wherever the water is going to go.
Thanks, Rob. And then Guy Linné asks a similar question. Controlling water in the boiler is one thing, but where's the data on cooling tower water? And Guy, we we originally intended to test this technology on a cooling tower, but frankly, as Dan mentioned, being the healthy skeptic, when we had the first failure of the heating elements because of the incorrect sizing of the technology, we decided, hey, we'll risk redoing this on a domestic hot water system, but let's not risk this on our cooling tower. And so we did do the cooling tower, and then subsequently, and Daniel Wong, you can help me on this, but I think subsequently also the Moss now gets its chilled water from the new Salt Lake City Courthouse anyway, so the cooling tower and the Moss is kind of no longer applicable. Is that right?
That is correct. Our cooling system was tied to the new district courthouse that was built around that same time. And so we actually, as we were finishing up the MNV for this particular project, my cooling tower was in the process of getting shut down, and we stopped using it. Guy, I would love to test this on some cooling towers somewhere also, just to see if this is something that would work. But we haven't gotten to that point at this point.
And we do have cooling tower applications across the world, that have, have been running for years, so we have those.
Do you have any studies or anything like that on those?
Let me check and see if we actually have any studies. To my knowledge, other than customers, just verbal or emails or stuff that, everything's running well. I mean, there's really not been a study like yours.
Sure. Okay. Thanks, Rob. And then Kenneth Raby. So what exactly is this device doing with the calcium? And Rob, that's probably a question for you again.
Yeah, yes. In water, you have calcite and aragonite. It's the two forms of scale. Calcite is the sticking and adhering form of scale, and the aragonite is the non-sticking, non-forming form of scale. And what we do is the water goes over the alloy. We keep it suspended in the aragonite state. So basically, the calcium carbonate, if you test the water, no matter what the hardness is going to be the same. because we didn't take out the calcium carbonate. All we do is formulate it into the aragonite state so it stays suspended in the water and doesn't stick or adhere anything after that. And we've done static tests before where we did a 3-month to 4-month static test where water was converted and it was still in the aragonite state. If water is not reheated multiple times, we have an application where we're treating over 1 mile of pipe work in a building, and it's working without any failures. So basically, we just keep the aragonite suspended in the water.
Thank you. And then Richard Sharma, what about the lifetime of the device installed? How long does it generally last? And what causes the failure if it does fail?
We'll tell you the life expectancy is 15 to 20 years. The oldest one we know of lasted 26 years. And Dan could probably back me up, I'm not an engineer, but over time, polarities in metals change due to age, not usage, not hard water, anything like that. The polarity of metals change. So when we cast these alloys, they're cast with a certain polarity, and just Mother Nature over time will change it. Like I say, so we tell everybody it's a 15 to 20 year life expectancy. Like I say, 26 years is the oldest element we know that lasted.
Yeah, this is Dan Howitt. Rob, since you referenced my name, I just have to say that chemistry is not my strong suit.
I understand that.
Okay.
And let's see, I'm going to skip down a little bit because we've got some questions answered. So, well, I think Rob's explained how it works. So let's see. Question for Daniel Wong. Were water softeners used at this location prior to this test?
We actually were just considering whether or not we would use water softeners for the hard water at this location. This project came into being just as we were considering that, so we never installed water softeners here. We did have water softeners on our condensing water up at the cooling tower, and they were working well for the cooling tower before we shut that off.
Thanks. Next question, if the system has a drain, so this might be applicable for a cooling tower, is argonite okay for public water systems for, passage or disposal into public water systems?
Yes, it is.
Okay, thank you.
We have all of our NSF certifications for potable water.
Great, thanks. Dan Lewis asks, is this test on a domestic hot water system? And that is the case. I don't know, Daniel, if you have any more details on the system, but
yeah, it is our domestic hot water, incoming city water, and return water that is getting heated and then sent throughout the building.
Okay, Rob, probably a question for you here. Kenneth Raby asks, if this is changing the calcium to argonite, how does the size of the system cause it not to work? If semicolon, if it's too big as it relates to this water heater. Originally, 1 1/4 inch was installed, wasn't working, but yet the 3/4 was installed and it worked. So could you explain that process, if you will?
Yes. Unlike most plumbing systems, bigger is not better with us. We need to be in a range. It doesn't have to be precise on the GPMs of flow because we don't need the water just to crawl across the alloy. We need the water to actually flow and turbulate around the alloy so that most of the water molecules will touch the alloy at some point in time. Now, you can also have too much flow and you get laminar flow so you don't get the interaction with the core. So when you get the proper, and it's a wide band, it's not, like I say, it's not very just 1 gallon per specific. So you just need that good flow of GPMs across the alloy to convert the molecules from calcite to aragonite.
Great, thank you. Anthony Phelps has a question that hit me as well. Seems like there should be a larger element that could be placed on the incoming domestic line that would save all devices downstream, or in other words, could this be kind of as long as it fits within your size regime, Could you, Rob, have your element placed kind of in the domestic water supply coming into a building and then have it basically treat the building?
Yes, we do. Yes. In fact, most applications, most of our devices generally go into public buildings like hospitals or nursing homes, a lot of commercial stuff where we do point of use or point of entry, either one. And so if you go in, and let's just say if we had done that original building, we would put one on the point of entry based on approximate flow, but we would still had one on the recirc line coming back to the water heater, because when the water is heated multiple times, whether it's just going round and round, the aragonite can revert back. So in an application of a building with no recirc lines, you can get by with one unit. But if you have a hot water recirc line like we did here, we would have treated just the recirc, not the main water coming to the building. And typically the recircs are smaller, as we know.
And I'm jumping down a little bit here because I think these questions have been answered. James DeMoy, I apologize if I butchered your name, says he was late to the presentation, and what device company is this? So Rob, if you would give just a quick 1-minute synopsis of your company and this device, that would be great.
Yes, we're Fluid Dynamics USA. We manufacture our product over in England, Fluid Dynamics Limited over there. We've been in business since 1973. We are the only non-chemical water treatment that uses a catalytic process in the world. We have applications in, I've lost count of the track number of countries now, but we do everything from your Keurig coffee dispenser to cooling towers, boilers, condensers, all types of applications, whether it be hospitals, hotels. We are the catalytic water treatment company in the world.
Great, thanks. Next question, Damon Cantrell. Are all new construction projects being mandated to include this in their design? And there's several questions here, so I'll read them all and probably do my best to answer the question. If not, is it the response of the regions to retrofit if they wish to use it? Or is there a funded established for this? And then in a performance-based environment of our contracts, I'm not saying O&M contractors open up the hot water heaters every year and clean the calcium. I suspect they simply run to fail. Question number one, is this being mandated? No, it is not. What we do have within GSA is we have what is called our P100, which is basically GSA's internal performance specification. And just this last year, we have a requirement that's within that performance specification that projects must consider and actually utilize in their projects at least 2 GPG technologies. And it's basically up to them to select those technologies. Again, I mentioned that the P100 is a performance specification, so we tend to not mandate specific technologies as well as specific manufacturers, even if it's a sole proprietor like Fluid Dynamics in this case. We say, hey, the technology works, but GSA as a federal agency is not in the business of championing and manufacturing a specific project or product. The regions can choose to, uptake these technologies on their own. We are in the process of putting together we have submitted to leadership kind of a deployment, recommended deployment program. And if that were to be approved, there's a possibility we might see what we do call fence funds to help with the deployment and adoption of GPG technologies, but that does not yet exist. And then I may just ask Daniel Long to weigh in, but I think you're right with, your typical domestic or I'll say commercial hot water system, typically they wouldn't be cleaned out, but in a location like Salt Lake City with such hard water, you just learn that you have to do it because of the conditions under which you're operating. Daniel, I don't know if you could speak to whether you do that in other buildings in the region. Your whole area probably has hard water, so it's probably the case for Salt Lake City area. But
yes, we do. Our O&M contractor knows that the situation with our water, so they are regularly checking on our water heaters and just validating that we're not having any major catastrophic failure in other places. So they are checking our water heaters on a regular basis here.
Next question, and Dan Howlett, I'll let you share your answer. Ken Raby, is this for potable water or for heating water?
Yeah, this is Dan Howlett. The system that we tested it on was a domestic potable water system. As Rob mentioned, this system has been certified by the NSF for use on potable water. The water can flow through this and you can still consume it safely. As an evaluator, I think it's safe to extrapolate and say that if you use this on a domestic heating water system, not potable but heating, you would see the same effect as far as the calcite reduction.
Great, thanks. And then Galane, were there other non-chemical treatment technologies tested or only this one? In this specific project, Guy, we only tested this specific technology. Paul Zambone, can you provide brand names, model numbers, etc.? And because GSA does not champion specific technology vendors, what I may do is if you go to the report that's posted in the appendix, there is contact information there, the name and contact information for the company. So you can go to the GPG website and look up this study and then get the contact information there, and that your desired information can be provided.
It's Fluid Dynamics USA is our website, and the test results and all of our contact information is there. It's fluiddynamicsusa.com.
Thanks, Rob. Let's see, going through these questions to see if they've been answered.
I'm sorry, I said Fluid Dynamics. It's scalepreventionusa.com. We changed it both work, but you'll go directly. I'm sorry, it's scalepreventionusa.com. They both work, but that's the new website name.
Thanks, Rob. Let's see, Ronald Whitley, is the quality of the water compromised for portable purposes by using this device? And I will say that, again, this device was used on domestic hot water. However, it sounds like, Rob, when it's used in a domestic service supply for an entire building, it doesn't seem to cause problems for potable water service.
No. And like I said, we're in hospitals, nursing homes, and we're in 2 pharmaceutical plants protecting the inbound water for pharmaceutical plants. So we do a gambit of everything. A lot of food manufacturing.
Okay, thanks.
And this is Daniel Wong. This is Daniel Wong in Salt Lake City. This is a federal courthouse, so our chambers, as you may know if you work in a similar situation, are fairly sensitive to major changes. They have not communicated to us that there is any change in the quality of the water.
Thanks, Daniel. Michael asked, did I understand this could not be used in systems with high iron? Rob, any experience with areas of high iron?
Yeah, anything over 4 parts per million of iron, you need to treat the water for iron prior to going through our unit. Because what happens is, everybody knows iron will coat most anything it touches. And so what it does, it'll coat the alloy and keep it from working. But 4 parts per million of iron is kind of iced tea colored water most of the time. So, and typically it causes other issues. So you're probably treating it anyhow.
Okay, great, thanks. And I think that answers another question further down. So I think we've got one last question. Will the slide presentation be available to us? And yes, it will be. And it's available on under a very long URL. So Andrea, is this something you could send out to all the attendees?
Yes, and I think that it's posted in the chat window there for you. So it's under, if you go search for the GSA Proving Ground and go to Outbrief Webinars, that's where you can find all of the slide presentations as well as recordings from past webinars.
Great,
and we'll
thank
be
you.
posting that later this week.
And I think that's it for this presentation and the Q&A session.
Yeah, great.
Thank you, everyone.
Thank
Anything,
you.
Andrea, you want to do to wrap it up?
Just one thing. Thanks to all the presenters and to all the great questions. It was a really interesting presentation. So again, we should be receiving a short survey, post-webinar survey, and if you can complete that, you can request continuing education credit. If you don't receive the survey, you can reach out to me or to Michael Hobson to get a copy of the survey and request the continuing education credit. So thanks again to all of you and to all the great participation.
Thank you, everyone.
Thank you.
Thank you. Bye-bye.